Good morning, everybody. So this is it. This is a white paper. There are a number of copies out in front of the posters. We have it in 3 languages: German, English, and French. I have the pleasure to present some of the key findings of the white paper on behalf of a bigger authorship team. So you have all the authors here. And this is a work of 5 SCCRs, so this is a joint activity. And 7 institutions contributed to this white paper, namely PSI, ZHAW, ETH, University of Geneva. I also see a co-author here. And the Hochschule in Rapperswil and Lucerne, and also EMPA was involved. And actually, many of the background has been already elaborated on by the other speakers already. So we do have at the moment 60% of the emissions in Switzerland are being emitted in the building sector or in the mobility sector, and well, the CO2 emissions, the CO2 generation is almost carbon-free. And we have the climate policy, which is now in Switzerland with the law and the debate, which is very ambitious if you look at the Paris Accord. And the ambition in Switzerland is to reduce the emissions by 2030 by minus 50%, and in the long run to become carbon-free. That is very ambitious. And also the energy policy. So the Energy Strategy 2050 imposes some challenges for the Swiss energy system, specifically for the electricity system, where the phase-out of nuclear power is laid down, and an increase of solar, wind, and other renewable energy generation up to plus 11.4 terawatt hours by 2035. So, and it has already been mentioned that we need more flexibility and we need appropriate greenhouse gas mitigation options to tackle these challenges which we face. And there exactly the white paper comes in, and the objective of the white paper here is to collect existing storage on one of these emission mitigation and flexibility option, which is Power-to-X, and collect this available knowledge and to be a kind of a information channel for a broader audience, a technical-oriented audience, and that's why we established this white paper. When we talk about Power-to-X, we see this as a kind of a subordinated expression of systems which convert electricity into synthetic fuels through an electrochemical process. And in our analysis here, we have not included power to heat. So it's really power to methane, power to liquids, power to hydrogen. So, and this white paper actually, it looks at a very broad perspective, or at multiple perspectives, on Power-to-X. So we look at the power system perspective, the gas market perspective, we look at CO2 sources, we look at the legal frameworks, and we look at the environmental impacts. So we try to capture this from a very broad perspective and to combine the existing knowledge here. So I would like to give a brief overview on the Power-to-X pathways, and we laid this out in the white paper very clearly, and this is also the information of the broader audience. What is Power-to-X actually? So actually, there are a lot of pathways. So one pathway is to produce hydrogen from electricity and to use the hydrogen as an energy carrier in end-use sectors. And this is what you see here on that slide. And you can use the hydrogen in a number of end-use sectors for heating purposes, for industrial purposes, and for providing mobility services. In the case of mobility, hydrogen really represents an indirect electrification option, because in the end, if you use an electric motor as a drivetrain in your car, then this is an electrification, but this is an indirect electrification because we fuel the car with hydrogen. There's another, apart from the hydrogen pathway, there's another big, let's say, compound of pathways, which is the synthetic fuel production pathways based on hydrogen. So we have, again, the conversion of electricity into hydrogen, and then by adding nitrogen or by adding carbon atoms, we can produce synthetic hydrocarbon fuels or ammonia. And also these synthetic fuels, they can be used in multiple energy or for multiple energy services, be it mobility, be it heating, be it also in the chemical sector or other industry sectors as well. Very important is that here the properties of many of these synthetic fuels are similar to the fuels which we have today, the fossil-based fuels. So they can be a very good substitute, which probably is also important for sectors like aviation sector, where a substitution with complete new energy carriers is rather problematic. So what we need for the synthetic hydrocarbon fuels is a carbon source. So the carbon source could be from power generation, could be from biomass, could be from industry like cement plants, but could also be from direct air capture systems. And the costs of these are very different, but this has the opportunity here to provide carbon atoms to produce synthetic carbon fuels here through different reactions. So actually, to use the carbon atoms from emission sources, and for instance, emission sources from biomass and direct air capture, really makes it possible to close the carbon cycle with this technology. That's an important point. But when we talk about the CO2 sources, and here this is a study led by Sinan Teske, then we have to look at the location of the emission sources. And what you see here in the green chart, these are all CO2 emission sources in Switzerland from that study, which are 7 million tons CO2. These are stationary emission sources. And you see that many of, a big share comes from cement plants. We have 6 cement plants. And waste incineration plants, where we have roughly 30 waste incineration plants. And these two together, they make up for almost all the stationary emissions here, big emission sources here from that study. Where you see sewage treatment, these are here the lower graphs, depending on the size of the community, are rather small. And basically, this means that in the cement plants here, if we use the CO2 from the cement plants at the current level, we can produce roughly 15 terawatt hours of synthetic natural gas. If we use the waste incineration plant emissions, we can produce 23 terawatt hours of synthetic methane. Of course, and what has been stressed already, here it's also depending on the infrastructure. Where do I locate my power to X plant? Is it close to the production side of a renewable energy, or is it close to the emission source to produce a synthetic hydrocarbon? So there's a location aspect here, and this also relates somehow if I can use existing infrastructure or not, or what are the costs of using existing infrastructure or not. So basically, the core component here in all this setup is the electrolyzer. This is a very important component. You know this, there are 3 different types of electrolyzers. You have alkaline electrolyzers, which are the incumbent electrolyzers today. We have polymer electrolyte membrane technologies, which is an upcoming technology. Usually these are smaller with a higher power density, but also a higher efficiency, coming also at higher costs at the moment, roughly twice as expensive as the alkaline electrolyzers. But our cost assessment, which we did for these technologies, suggests that in future, the costs between alkaline electrolyzers and PEM electrolyzers would converge and would reduce compared to today's level. We have another very new electrolyzer technology. This is solid oxide electrolysis cells. This is a high temperature technology which where literature suggests that high efficiencies are possible and you also can run them in reverse mode. What is common to all electrolyzers is you need a supply of low-cost electricity, because electricity costs here make up for about 50% of the hydrogen production cost, or even more in some cases. So, and to come to a reasonable or to rather lower generation costs for hydrogen, you need also a couple of thousand full load hours. It's not sufficient to run the electrolyzer only if there's excess electricity, because then the part of the capital costs is rather high. So the current costs of electrolyzers are on average, based on the literature that we have looked at 144 Swiss francs per megawatt hour thermal for hydrogen. And this is above the cost of current steam methane reforming, which is a traditional technology used in industry at large scale at the moment. The future cost range for electrolyzers suggests we come into the range of steam methane reforming in the year 2050 or beyond. Also coming to, or related to the comparison of steam methane reforming and electrolysis is the greenhouse gas performance of hydrogen production. And here you see the comparison of the CO2 or the greenhouse gas intensity, and here you have steam methane reforming, and we compare this to different electrolyzers operated on renewable energies. Here this is wind and PV, and these are results from life cycle analysis. And you see that compared to steam methane reforming, we do have lower life cycle emissions if we run the electrolyzer on wind and PV. If we run it with a Swiss electricity mix, as we have it today, we also compared to steam methane reforming at a better greenhouse gas performance. But if we would, let's say, import electricity from the neighboring countries with an average ENTSO-E electricity mix, the overall greenhouse gas performance, it's working here, yeah, is worse than compared to steam methane reforming. So it matters where the electricity comes from. When we looked at the Power-to-X technologies, we looked at the different markets. So what are the opportunities of Power-to-X in different markets? And we looked at electricity market, gas market, the industry sector, and also the transport sector. And I will be very brief. In the electricity, we see that actually the power-to-gas technology is compared to other storage technologies, which are for short-term storage of electricity, so in particular pump storage and battery systems. Power-to-gas systems usually are more expensive. And for long-term storage, so for seasonal storage, then power-to-gas systems, they can reach at lower levelized storage costs compared to other storage systems. But we see a big rollout of short-term storages at the moment. We have pump storages available, but we see more battery systems coming online for the short-term storages. And there we have to say that the storage costs of battery systems are much lower compared to Power-to-X systems. You see that the average storage cost here, so it's storing electricity and re-electrifying again, we come at about 400 francs per megawatt hour electric. So this is way above battery systems. We also see that actually some Power-to-X systems can be operated very flexible. That means they are technically able to participate at ancillary services markets to provide reserve capacity, for instance. However, the revenues you can get from the ancillary services market is not sufficient alone to operate a Power-to-X system. So that improves economics, but it's not the absolute game changer here. If we look at the at other flexibility options in the system, for the seasonal balancing, we also have, for instance, natural gas combined cycle. So if we, let's say, install a natural gas combined cycle and just operate it in winter to let's say, to compensate reduced electricity production from renewables, then this can be made at comparably lower costs. And if we also regard electricity imports, and this is a statistic number here of 40 francs per megawatt hour, importing electricity can be even lower, and the spreads between the seasons of electricity price at the moment are relatively low. If we look into projections of electricity prices for the future, we see an increase in electricity price, can be doubled by 2030, for instance. But still, we are in a range, also at high electricity prices for imports, exports, actually where today's cost for the operation of Power-to-X systems just in the electricity market are much higher. In the gas market, so actually the current price levels of natural gas are around, across all consumers, at 70 francs per megawatt hour. And this is roughly 3 times lower than the current production costs of power-to-methane. And when we look a bit at specific consumers, we can see that some of the consumers are willing to pay a higher gas price for green gas, or for biogas, for instance. And there we see already, well, there we have price levels of about 140, 160 francs per megawatt hour. And there we see already that the costs of the power to methane come closer to these kind of price levels. But still, this is a question, what kind of additional costs we have for transporting the methane in the grid. Because this is a price level at the consumer, but this is a methane production cost. We see that from a legal perspective, because we also looked at the legal perspective, we see that actually the current laws actually allow to feeding in synthetic methane also in the lower grid levels. So from that perspective, there's at the moment no, let's say, no barrier to incorporate power to methane, except from the costs. From the transport perspective, we see that we see a high energy density of synthetic fuels. So this is similar to the properties of current fossil fuels. When we compare the costs, and here you have again the costs for synthetic methane, which I just showed on the gas slide as well, because this is also a potential fuel in the transport sector. And here we have the costs, the production cost of synthetic liquids. So they have here a range between 200 and 400 francs per megawatt hour. So with an average of about 270, 280 francs per megawatt hour. So this is comparably high. And when we compare the costs to fossil fuels, the cost for synthetic fuels are 2 to 3 times higher compared to the fossil fuels today. We also see that if you, for instance, build a new hydrogen infrastructure or natural gas infrastructure to fuel the cars, then the costs of this infrastructure depends also on the intensity of the usage. So how often, how many cars do you fuel with it? And if you only have few cars, then these kind of infrastructure costs can be also a very high share in the overall costs to provide the synthetic fuels. If we compare synthetic fuels to battery electric vehicles, which is a very often discussed carbon mitigation option in the mobility sector, we see that 3 to 4 times more primary energy is needed for Power-to-X fuels compared to the direct electrification of mobility. Again, from a legal perspective, the current law in Switzerland says that hydrogen and synthetic hydrocarbons, which are produced from renewable energies, are exempted from the mineral oil tax. Well, it depends on some environmental criteria, but in principle they are exempted from the mineral oil tax. So this is a promotion to these fuels. EMPA did a study on the comparison of the total cost of ownership of different mobility options, and here you see this is the trucks, and you see diesel trucks. You see synthetic diesel, so Fischer-Tropsch diesel. You see the costs for synthetic methane, and you see the cost for hydrogen. Since hydrogen would be an electric drivetrain in the truck, at the moment it would be exempted from a road tax, from the Schwerlastabgabe. That would make them competitive, but at the moment it's very unsure if this exemption remains also in the Swiss law. So there's a kind of uncertainty involved in this. For the cars, this is the lower part here, we see that actually compared to gasoline and to battery electric vehicles, which are the first two bars here, we see that synthetic methane leads to 20-25% higher costs in principle. If one is able to achieve scale effects, one gets down the costs here, but still it's very difficult to be competitive with a battery electric vehicle and with the current gasoline vehicles. What is specific about the car sector is that actually almost 100% of today's trips in Switzerland, because these are mostly short trips, and this is what you see here, almost 100% can actually be performed with a battery electric vehicle with a sufficient high range of the battery, here 400 kilometers, and then you can actually make 100% with the electric car. But this share declines the higher the weight of the vehicle. So with a medium size lorry, you have around 55%, and only 4% with a heavy duty vehicle, with a heavy duty truck, actually. When we look at the different markets, we see that it's very important, and this is a benefit of power-to-gas systems, that you access multiple markets. So that you make use of providing flexibility to the electricity system, that you provide clean fuels, and where possible, that you reuse CO2. So it's important for Power-to-X to access multiple markets and also to make it economic beneficial. And there we have again the legal aspects. So since it's based on hydrogen, and hydrogen is based on the electricity supply costs, it matters if you pay grid fees or if you don't pay grid fees. This is a very important driver for the economics. So the legal framework has a very important role, what markets you can access and where you locate your Power-to-X facility. This is just a picture looking into 2050. And yes, I acknowledge that this is a picture one can talk quite long time about. And this picture shows you, for 2050, hydrogen pathways, actually. And it starts with electricity that goes into hydrogen, that is used in an electrolyzer. You have some electrolyzer losses, and you produce hydrogen. And here, this is a climate scenario. So this aims at a reduction of CO2 emissions until 2050. And here we produce 3.6 terawatt hours of hydrogen. And this hydrogen is, to a large extent, directly used, particularly in the transport sector, but also for stationary applications. A part of this is shifted seasonally, just to provide seasonal flexibility to the system. Here it's about half a terawatt hour, which in the end also goes again to the demand sectors. A smaller part here of the hydrogen is used for methanation or goes directly into the gas grid. So what we see in this picture here, without going very detailed into the number, is that hydrogen satisfies demands in multiple sectors. So it's a universal fuel. It can be transformed into many other fuels as well, and that it can contribute to achieve climate and energy policy goals cost effectively, because this is the background of this kind of calculation here. If you're interested in the findings on the innovation policy, because I skipped this slide now, I invite you to have a look into the white paper. And I would like to close with the key recommendations which we concluded in our white paper. So obviously, Power-to-X systems rely on very stringent climate policy. We have at the moment some ambiguities in the regulation, in the legal framework, and these should be eliminated because these represent a significant uncertainty for the investments in Power-to-X. We need to upscale the pilot plants to commercial plants. This is important. This also relates a little bit to the innovation policy, because we need to demonstrate the feasibility of the entire chain. So from using the electricity, converting into hydrogen, maybe also using CO2 emissions from a stationary emission source, for instance, and then converting into synthetic fuel. To demonstrate this, we suggest to establish demonstration projects which really show the feasibility of the whole chain and not only just a fragment. And possibly also to complement this with market studies, which actually then show the implementation and the rollout of these technologies in a broader energy system. With this, I would like to thank you, and I invite you to go to the poster and also to take one of the white papers. Thank you very much.